You probably heard a lot about functional programming lately, so what is it and why should you care? Functional programming is definitely something you want to have in your tool belt. If you come from an OP background or you're just starting out, this video will clarify the what and why of functional programming. You will learn concepts like pure functions, function composition, and partial application. I will also talk about some new and some resurfacing trends in the software development ecosystem that favor functional programming and the functional way of thinking about software. By the end of the video, you will learn powerful new skills and a different way of solving programming problems. So why would you bother learning functional programming? Well, first, there are some trends in software development and software architecture that favor a functional approach. Think of microservices and how they compose together. Think of React hooks or Vue.js composition API. They both promote the idea of reusable, composable functions. Even in CSS, many people now prefer libraries like Tailwind CSS, where you compose styles to get the look you want, rather than fighting with a rigid CSS library. This idea of composability is also at the heart of functional programming. And let's face it, even in OOP, the convention is to favor composition over inheritance. Well, that's just functional programming with extra steps. Jokes aside, there is a bit of a learning curve where you have to switch your thinking from an imperative to a declarative style. You will have to stop categorizing objects into classes and instead start thinking about actions and flows. However, the nice thing about functional programming is that you don't have to give up anything. You don't have to go all in. You can pick and choose which of the concepts from functional programming you want to apply. You can even apply some of these principles in an OOP codebase. So there are only benefits in adding functional programming skills to your toolset. So what are some benefits of functional programming? Functional programming helps us write code that is, well, first reusable, easier to comprehend and debug, more testable, and less error prone. Indeed, functional programming has its roots in mathematics and computer science, specifically in lambda calculus and category theory. The truth is, you can start applying functional programming principles at any skill level without much mathematical knowledge. Yes, look, I'm terrible at math, and here I am talking about functional programming, so seriously, don't let that get in your way. So let's get some of the more boring stuff out the way first. Functional programming should not be confused with procedural programming. These terms are sometimes used incorrectly, interchangeably, but in fact they are quite opposite. Procedural programming, you send the exact instructions that tell the computer step by step what to do. This is sometimes also called imperative programming. Think of C, Pascal, or Fortran. And if you haven't heard of those, well, then lucky you. Functional programming is something completely different. It promotes what is called a declarative style of programming, meaning the instructions you give the program are focused on the actions or the outcome, and the functions themselves hide away the complexity. Think of the functions as Lego blocks that you can reuse and combine in order to get to the desired outcome. This approach is powerful, robust, and if I may, much more elegant. It can also be more concise and easier to maintain than the alternatives. Let's look at the following example. On the left, you have imperative code. You usually have to read it in its entirety before you understand what it does. The code on the right, however, is way more readable. You can immediately understand what it does without requiring you to read the whole thing. It's also more concise. Now let's talk about the most important thing in functional programming: functions themselves. Specifically, pure functions. In functional programming, functions take the main stage. They are usually pure functions. A pure function is a function that first always returns a value. Second, it calculates the return value based only on its arguments. And third, it doesn't mutate any existing values outside of its scope. In other words, pure functions promote writing clean code by having a single responsibility, so it is only used for its return value, not having any side effects, it uses only its arguments and nothing else. And third, having referential transparency, which means when you call the same functions with the same parameters, you will get exactly the same result. As you can see here, the function could be a black box. For a given input, it returns an output. The focus is not on the implementation details. Another advantage of pure functions is that they are intercompatible, and this will become more apparent when we start talking about function composition. Of course, you can't build an application with only pure functions. At some point you will have to write something to a database or make a network call or mutate the user interface. However, the more pure functions you have in your code base, the easier it is to maintain and test. When structuring your code base, the core of the application should be composed of pure functions. Database mutations, DOM manipulations are side effect inducing functions. This should be kept to a minimum, and more of your business layer, the logic of your application should be happening within these pure functions. The next important concept to understand is that of the higher order function. So higher order functions are functions that either take another function as an input or return a function as the output, or both. When writing functional code, you need to start thinking about how problems can be broken down into smaller steps or a set of functions. This becomes easier with practice, of course. These functions can be chained together, nested within each other, and passed around as arguments. This concept is also called functions as first-class citizens. One such example is the array.map function. As you can see, it takes another function as a parameter. We call the passed-in function a callback. Knowing this, you can apply a concept named partial application. In this example, we have a function that adds a discount to a product. It receives a percentage discount and a product, and it returns a new product with the discounted price. And you would use it something like this. Now imagine that instead of a single product, we have an array of products to which we have to apply a 20% discount. You would do that using the array.map method, and you would pass in the discount percentage and the product. However, this is not as expressive as it could be. Let's improve this a bit by using partial application. Let's create a new function called addDiscountPartial, which only takes in one argument, and that is the discount percentage, and returns another function that requires a product, in a sense waiting for the parameters to be applied one by one. We can then use this function to create other functions that apply various discounts. Then we can pass these new functions to our map, benefiting from the shortened syntax, because if the callback accepts a single parameter, it automatically passes the item in the current iteration. As you can see, this is a bit more expressive. And more importantly, you can see that functions that take in and return a single parameter or value are more compatible with each other. I've seen in many places this technique called currying. However, this is in fact partial application. Currying takes this a step further, as you will see when we look at it a bit later. With all that out of the way, we finally get to the most essential thing in functional programming, and that is actually composing functions. The previous concept we talked about, partial application, was useful for creating new functions out of other functions, or new functionality by partially applying some of the parameters. Now, we will go a bit further and use the concept of a pipe. You might know this intuitively, or even used it in the Linux command line, for example. With this technique, you will pass the output of a function as the input to the following function, while the output of the last function is the output of the whole, creating a pipeline of functions through which the data flows. In order to use function composition, we need to implement a couple of helpers named pipe and compose. They are both pure higher-order functions. Let's check them out. Here we are using the REST parameter syntax because our pipe function will have a variable number of parameters. We don't know how many. We then return another function that accepts the initial data, which is then passed as the initial value to the reduce method. Using reduce, we iterate over every function passed and executed and send the result to the next function. Brilliant. Compose works much in the same way. The difference is that it applies the functions in the reverse order using reduce write. If you are unsure about how array reduce works, you can subscribe to this channel for a future video going over the most usual array methods. And finally, let's look at currying. Let me start by showing why we need the curry helper method in the first place. As you saw, function composition favors functions that take a single input parameter. However, in some cases we may have functions that take in multiple parameters. How can we take these functions and transform them into functions that take a single parameter at a time? Let's take as an example this function that takes 3 parameters. How can we apply the 3 parameters one by one? Well, it's simple. We already talked about this. Partial application. However, as you can see, This nesting gets stupid pretty fast. This is where currying comes in. Curry is a helper function that can take a function which accepts many parameters and return another function that takes the parameters one by one until all the parameters are exhausted. We call this the curried version of the function. Let's look at an implementation of curry. As you can see, the curry helper function takes a function as the parameter. It then returns a function that can take a variable number of parameters, thanks to the REST parameter syntax. Inside this function, we can check the total number of parameters required, using the length property of the passed-in function. If the length is greater than the passed-in arguments, it means that there are still arguments that have to be passed in which case we return another function that expects the rest of the parameters by calling this function recursively, providing it all the parameters accumulated so far. Finally, once all of the parameters have been provided, we execute the original function and return the result. Let's look at a practical example with all of these concepts combined. So here I have an exercise file. It's written in TypeScript. If you're not familiar with TypeScript, just ignore the type annotations. It's still valid JavaScript without them. Also, I might create some videos about TypeScript in the future, so get subscribed to see those. I've defined a type here, a data structure representing a car. It has a few properties such as year, make, model, power, and acceleration. Now let's imagine we are building a dashboard containing charts and statistics about cars. Our input data is an array of cars. I have 6 cars here with various stats. Let's build a function that gets the item with the maximum value from an array. Let's call this function getMax. This function takes a generic type. It accepts a couple of arguments. First, the comparator, which is a field from the type we are operating on, and second is the array of items. It returns a single item. We will implement this logic using reduce. So items.reduce, pass in a callback. The callback has 2 params, accumulator and the current item. We then check if the current item is greater than what we have in the accumulator. The callback has to return something, so we return which is greater between the item and the accumulator. Finally, we return the whole thing. So let's use this function to find out the slowest car, which would be the car with the maximum acceleration value. And apparently that is the Mercedes. We can also reuse this function to get the most powerful car. Now this function is alright. However, like we talked about, functions that take multiple arguments are harder to compose, and we definitely want to compose these functions, as you will soon see. Let's curry the getMax function to obtain the curried version of it. If you remember, the curried version takes the arguments one by one, so we can then apply the first parameter in order to obtain functions that require the second one. We can reuse this function to create a few other functions. Let's create a couple of more helper functions. One to sort the items in an array and one to limit the number of items. First, the sort items by function, which returns a new array without mutating the original. We don't want to sort the original since we might use the original array in multiple places to get different statistics. We achieve this by creating a shallow copy of the array using the spread operator, then applying the sort method to that. Let's cast these two numbers so we get rid of the type errors. Then, let's implement a limit function. This function takes in the limit and the items and returns a new sliced array. Now imagine we want to get the most powerful car out of the top 3 newest cars. We can achieve this by piping together a few functions as we talked about. First, let's start by creating curried versions of these helper functions. So we need a way to sort by year. We can use the curried sort by function and apply year as the first parameter. We can create a similar function to sort by power. Finally, let's compose these functions together. Inside a pipe, let's first sort by year, then plug in the array of cars as a parameter to the pipe. As you can see, the result is the sorted array. It seems that we've sorted the array ascending. Let's fix that real quick since we want to sort it descending. Next, let's create a new function called limit3, which we obtain by applying 3 as the first parameter to the curried version of our limit function. And we suddenly have a sorted array limited to 3 items. Finally, let's add the function we created earlier to get the most powerful car. And as you can see, the Mercedes is the most powerful of the top 3 newest cars. Let's solve a similar problem, this time using compose instead of pipe, so you can see the difference. So the main difference is the order in which you apply the functions. It's exactly in reverse compared to the pipe. The nice thing about compose is that the code reads in the same way as you would spell out the problem. So we want to get the newest car out of the top 3 most powerful cars. And again, it's the Mercedes. For our last exercise, let's create a function that applies a discount to a car. It takes the item to discount and the list. Then it returns the list with the discounted item in it. You will see later why it's important that it returns the whole list. We create a copy of the item and add the discount property to it. Then, using a combination of filter and the spread operator, we create a new array with the old item replaced with the discounted one. The result we want to obtain is a list of cars ordered by newest first with the discount applied to the slowest car. As you've probably guessed, we start by creating a curried version of the function we just created. Let's create our pipe, which will eventually return our result. Let's add to it the sort by year function and feed it the cars array. We need a way to apply a discount to the slowest car. For this, we create a separate pipe. In it, we use the function created earlier to get the slowest car. Now here is where it gets a bit tricky. We add to the pipe the curried version of the apply discount function, which expects as a first argument the item to discount, which is perfectly compatible with the first function in the pipe, since that one returns the slowest item. Add discount function, with this first argument applied, returns another function that expects the second argument, which is the array of cars. So the result of the pipe is the result of the last function, in this case another function. Then we can take the function that is returned from the first pipe and add it to the second one. Pretty cool. However, it's not the easiest to understand. Maybe we can do something a bit better by rethinking our helper method. Let's create an alternative version of the apply discount function, calling it very creatively apply discount to item 2. Let's have this function, instead of expecting the item to discount as the first parameter, it should now expect a function and the array of items. And it obtains the item to discount by applying the function to the items. The rest is exactly the same as before. Obviously, we need a curried version of this function, so let's create that. Now, we can create a simpler flow to get the same result as before. We can discount the slowest car by applying the first argument to the curried function, and that is the function which gets us the slowest car. Then we can create a simpler pipe that first discounts the slowest item, then sort them by year, feed in the array of cars, and that's it. A bit cleaner than before. Let's recap. We looked over a few important concepts such as pure functions and higher order functions. We also briefly touched on the concept of recursivity. Then, we went over some helper functions that allow us to compose other functions, such as pipe and compose. We also looked at currying. Finally, we used everything in a practical example. Everything you saw in this video might not make sense immediately. That's okay, and is to be expected. These are challenging topics, especially currying. They take some practice to start making sense. Don't forget to subscribe for more content like this. I leave you with a quote from John Carmack, lead programmer of the Doom video game.